Okay, great. Recording has been started. Now about unit number two. In unit number one, we have discussed lots of phenomenon about free space and the electric field intensity, electric flux density, Gauss law, divergence theorem, everything over there. And today we are going to start with unit number two, where we are going to see how electric field behaves inside the conductor, inside the different kind of material, dielectric materials. Okay. Why we want to discuss, because we know that air itself is an dielectric material. Okay, and we want to observe the behavior of electric field in various materials, and then we want to see how electric field propagates to the dielectric material, because we know that we do have capacitors who store some amount of energy in it. Okay, and talking about the stored energy inside the material, we need to see how electric field passes through it, how it propagates through it, how we can justify the Gauss law. Gauss law states that if we put some amount of charge on one surface and we keep another charge which is sorry, we keep another surface which is electrically isolated from it, an equal amount of charge but opposite in polarity is developed on the other surface. That is a principle of capacitance. Okay, why exactly it happens and how it happens and what are the different observations we are going to see in today's session. What I am going to do, I have prepared a very concise video for that purpose, and so that we will cover a lot of concept in next 42 minutes. Okay, the video length is of 42 minutes and we are going to see that video. So stick around, I'm going to play it, and side by side keep on making notes on your own. Okay, keep on making notes. So let me share. Can you see this one? E in
Yes, sir. Yes.
free space, conductors and dielectrics. Okay, great. So let me know whether you are able to listen to the audio as well. Let us start a discussion about electric field intensity in free space. Can you hear the audio as well?
येस सर. तुमचा आवाज आहे ना?
हो, माझाच आवाज आहे.
हो, हो. त्याच्यामुळे मी विचारतोय तुम्हाला.
it's it's my recorded video. Okay, I will play the video, and video length is of 42 minutes, so probably lecture will end at 9:45. Stick around.
येस सर.
Conductors as well as dielectrics. Till point we have discussed the behavior of electric field intensity or electric field density or flux density in the free space, where we consider the permittivity of the material or medium as epsilon 0. Do remember that if we are talking about the permittivity of the material, it has to be expressed in this way: epsilon 0, epsilon r. This is the permittivity of the free space and this is the relative permittivity. Okay, so when we are going to discuss about the conductors and especially about the dielectrics materials, so we have to consider the behavior of electric field in that material, in that medium or region, as well as along the boundary. We are going to see how electric field behaves along the boundary later on, but let us start with the discussion about electric field, okay, in the free space. Previously we have seen electric field due to a point charge cube, which was expressed as E bar is equal to 1 4 epsilon 0 r square air cap. Then a line charge distribution having rho L as line charge density. E bar is given as rho L upon 2 pi epsilon 0 r air cap. About surface charge distribution, which has rho S as a surface charge density. It is expressed as electric field intensity is equal to rho S upon 2 epsilon 0 a n cap. Very interesting thing is happening over here. You can look at the denominator part. Okay, I will concentrate over here. 4, 2, and here also 2. But electric field intensity is inversely proportional to square of the distance. Here, electric field intensity is proportional to the inversely proportional to the distance, and here electric field is independent of distance in between the source of electric field and the observation point. Very important thing we have to remember about this expression, the surface charge distribution we have considered for this is an infinite surface charge distribution. Then we have studied and applied a formula for a system having multiple type of charges. It is also usually called a superposition theorem. So we had system containing simple point charges, system containing line charges, then surface charges. This was understanding of the electric field, how it behaves in the free space due to various charge distributions. Then when we talk about material, those are distinguished depending upon different properties of the material. What are different properties of the material are? Let us a material with high conductivity, that is sigma greater than 1. Sigma is the conductivity, is referred as metals. अगर sigma बड़ा है बहुत ज़्यादा है, so those are called as metals. A material with small conductivity is called as insulator or dielectric medium, and a material with conductivity lies between metals and insulator are called as semiconductor. This is a very rough idea about the behavior of materials when we are considering the conductivity as a unit of measure alone. Indeed, we do have different measures as well for defining the properties of material, but for now, to keep our discussion concise, conductivity of the material is more, those are metals. If it is less, those are dielectric materials. And if it is in between metals and dielectric materials, then those are referred as semiconductors. Let us see how electric field behaves in conductors. Okay, this is a very conceptual topic. Okay, what exactly is happening and why it is happening, let us see. So, a conductor always have an abundance of charge, lots of free charges. Under influence of the applied external electric field, charge exhibits following behavior. What sort of behavior? They accumulate on the surface of the conductor. If let us say we do have a cylindrical shaped conductor, initially they do have some free charges. Okay, those are moving in a random direction. But as soon as we apply some sort of external electric field, they get oriented in certain direction. Okay, their random behavior is no more observed and they are having certain direction. But while these charges under the influence of external field, these charges first diverts towards the surface of the conductor. Means all the charges, if we are considering the electrons, first they accumulate on the surface of the conductor. This is also called as the skin effect, which will be studied later on. Okay, this is going to form an induced surface charge. Induced surface charge means it is created due to influence of external field. This induced surface charge setups internal induced field. ये जो charges तैयार हो रहे हैं on the surface, they have their own electric field, and this electric field is going to cancel externally applied electric field. Okay, कहाँ पे cancel करने वाला है? ये inside में. Okay, a perfect conductor, which do not exist practically, but as a theory assumption, it has conductivity is equal to infinity. Okay, this cannot contain an electrostatic field within it. A conductor is called as equipotential body, implying that the potential is the same everywhere in the conductor. This is based on the fact that the gradient of voltage, the potential, is nothing but electric field intensity is zero in the ideal conductor. Okay, so ideal conductor में क्या ध्यान रखना है? We know conductivity is infinity, as well as conductor is also an equipotential body. Okay, and do remember that the electric field inside, do remember this word, the electric field inside the conductor is zero, inside the ideal conductor is zero. Then we know one Ohm's law, very well known Ohm's law, V is equal to IR. Okay, so similarly I can express this one as also as V is equal, sorry, I is equal to V upon R. We are going to express the same Ohm's law but in different kind of understanding, which is expressed as J is equal to sigma E. Here J is current density, okay, which is analogous to current. Okay, E is applied electric field, which is analogous to applied voltage, and sigma E is nothing but 1 upon resistance, it is conductivity. So overall the formula talks about the same quantities, similar quantities, but this time we do have different notations. So current density is expressed as J bar is equal to sigma E bar. To maintain a finite current density J bar in a perfect conductor, that is our assumption is sigma tends to be infinity, requires that electric field inside the conductor vanish. Q the electric field inside the conductor vanishes due to induced surface field. ये induced surface मतलब create जो हुआ है surface field क्यों create हुआ था because our charges got accumulated on the surface under the influence of external field. Okay, तो अगर आपको current density finite रखना है तो मैथमेटिकली वी कैन रिलेट द थिंग्स कि भाई उसके अंदर का कंडक्टर के अंदर का इलेक्ट्रिक फील्ड मस्ट बी इक्वल टू जीरो अंडर एन assumption that sigma is infinity. In other words, electric field intensity inside the conductor is zero because its conductivity is infinite. If some charges are introduced in the conductor, these will move towards the surface and arranging themselves in a manner that inside field gets cancelled. भाई आप कितने भी चार्ज पुट अप कर लो, externally supplied charge insert करो conductor में, they will tend to flow towards the surface and they will be in equilibrium so that electric field inside the conductor will become zero. According to Gauss law, if we say that E bar is equal to 0, then the charge density rho v must be 0, where once again we are talking about the inside the electric field. That is our topic, electric field inside the conductor. Okay. We again conclude that a perfect conductor cannot have electric field inside it. So this is very important for a perfect conductor for whom its conductivity tends to infinity, electric field inside it is zero. Therefore, according to Gauss law, volume charge density is equal to zero. That means no charges, free charges exist inside the conductor, as well as since we don't have any electric field, therefore potential is also zero inside the conductor. But definitely, if the conductor is a practical one, it will exhibit some resistance, and these properties will not exist. Okay. Then the very interesting thing happens when we talk about the electric field in dielectric materials. Let us discuss about the diagrams. Here we have we have some an atom. Let us say this is a structure of an atom where we do have a positive nucleus and we have a cloud of electrons surrounding it. And we know that the atom, individual atom, is always electrically neutral. So we can say that the electric field, okay, electric field is equal to 0. But as soon as, okay, as soon as let's just say now we are applying external electric field, okay, external electric field. Well, this is a structure of an atom under the influence of the external field. So here we have assumed that, okay, if external applied field is 0, then atom exhibits an symmetry. Okay. But as soon as we apply external electric field, it has some change in the shape of its electron cloud. Shape of electron cloud. So since we are assuming electric field is in this direction, so we can say that, okay, some sort of positive terminal of the battery exists on the left hand side, and the electrons got attracted towards those positive charges, and the cloud is little bit shifted towards of the electrons. Okay, so I can say that in this region, the shaded region, we do have more amount of electrons compared to this region. We do have a little bit difference. So we can say that in this part of the atom now, we do have more amount of negative charge compared to this part of the atom. So we can represent it as a positive amount of charge. So under the influence of electric field, we can say that we have created a dipole. We have created a dipole separated by some distance d. Okay, and under the absence of external electric field, these dipoles are a random in a direction. But as soon as we apply electric field, these get some orientation depending upon the direction of the electric field. Okay, so all the things happens very interestingly inside the dielectrics, knowing that knowing that all the atoms are at fixed position. They do not move. They do not move. Dielectric materials do not have any free charges. Don't have any free charges. Okay. Whatever happening is happening to the electron cloud. Okay. Whatever is happening to the electron cloud around the nucleus inside the atom. Okay. Electron cloud, and due to that we are creating a dipole inside the dielectric material. Let us go through the text. The main difference in the conductors and dielectric lies in the viability of the charges. Charges in dielectric are not able to move freely and are bounded by atomic forces, but they can experience, this is very important word, they can experience displacement in their position under the influence of applied electric field. In presence of external field, electrons' center of rotation gets disturbed, and now symmetry is no more obeyed. The effect of electric field generates polarization effect in dielectric. जो dipole create हो रहा है, it is called as polarization. We create some sort of polarities under the influence of electric field, applied electric field. The molecules are deformed from their original shape, and each molecule gets some dipole moment. Okay, this creates an effective dipole inside the dielectric material. Okay. This dipole now contains two opposite charges separated by distance. This is called as polarization. Very important word, polarization. So individual atom electrically neutral. Atoms inside the dielectrics do not move. Dielectrics don't have any free charges, but as soon as we apply external electric field, a dipole is created inside an atom because the electron cloud experiences some sort of force. Okay, so with understanding of these, we can discuss. Let us consider this is a capacitor structure, parallel plate capacitor. Okay. So under the influence of electric field, let us assume that we have applied the positive charges right now. So we do have created lot of dipoles over here indicated by plus and minus sign. Okay, those are going to indicate the created dipoles or polarization inside the dielectric material. So these positive charges, okay, the positive charges on the upper plate will have electric field lines. Okay, electric field lines from the positive plate going to the another plate. Okay, so according to the Faraday's law or Faraday's experiment, we know that equal and opposite charge is developed on the second plate, as well as these small dipoles are creating their own electric field. Okay, their own electric field may be small in magnitude, but there are lots of dipoles. There are billions of atoms. Okay, so billions of atoms, even if they are contributing to a very minute amount of electric field, that is going to be a big number. So I want to give important point over here. First, as soon as we apply positive charges to the plate number 1 of the capacitor, we get electric field lines. Okay, let us say we do have a electric field lines. Second, this will develop negative charge on the second plate. Then what happens third? Let us write down something over here. Right now we do have amount of electric field equal to A in a downward direction. Okay. The next point is dipoles are created. Okay, or we can say that polarization of the dielectric material happened. Then we can say that electric field will be generated due to dipoles. Okay, due to dipoles, and this electric field will be in opposite direction to that of electric field generated by plate 1. So can I say that looking at point number 1 and looking at point number 5 and point number 1, I can say that there is some sort of cancelling effect. So I will comment that since both the electric fields do have opposite direction, the effective electric field inside dielectric medium will decrease. Very important observation. Okay, due to creation of the polarization. Now let us go through the text and some little notations. Polarization results in increasing the electric flux density. Okay, what is here? Electric flux density. Number of flux. Definitely number of flux lines increasing, but electric field intensity is going to decrease. Okay, so we can say that, okay, so d bar flux density, which was previously only epsilon 0 e bar, now will have increase in its quantity, number of flux lines. Okay, where p bar is a polarization. If material is following Ohm's law and linear the polarization in, means the material is throughout exhibiting the same amount of polarization, then we can say that polarization is equal to, let us say, xe epsilon 0 e bar. Okay, where Xe is electric susceptibility of the medium. Okay, of the medium. So putting these values into the expression of d bar, so we do have d bar is equal to epsilon 0 e bar plus ze epsilon 0 e bar. So taking out some constant, so d bar is equal to 1 plus ze and also the bracket epsilon 0 E bar, and here 1 plus ZE is called as relative permittivity, and here now D bar is equal to epsilon E E0. So probably now you have understood from the heck where relative permittivity comes into picture. So that was all part of atomic nature under the influence of electric field. Okay, so polarization in dielectric is quite interesting, but since no dielectric is ideal, therefore when electric field in a dielectric is sufficiently large, it begins to pull electrons completely out of the molecules and dielectric becomes conducting. What do you mean by no dielectric is ideal? Means it will have some sort of minor charges. Okay, major charges electrons रहते हैं conductor में, but electrons में in dielectric material we will have some free charges. Okay, some free charges that is going to flow through the medium under the influence of electric field, and as soon as we say that they flow, it becomes conducting. Okay, so therefore dielectric breakdown occurs. Okay, मतलब वो जो charges move हो रहे from one plate to another plate under the influence of applied field, your dielectric medium, in simple words I can say that it gets short circuited. Okay, and that is called as dielectric breakdown. Okay, when the dielectric becomes conducting, or in another words I can say that your applied electric field is so large enough that it is going to pull out the electrons outside the atom, outside the atom. So you can call it as a भाई आपका capacitor जल गया, okay, due to short circuit or due to heavy voltage. That is called as dielectric breakdown. And many times in real environments we have seen this phenomenon whenever your ground is being struck by the lightning. That is nothing but the dielectric breakdown. We do have some clouds. Those are having some sort of mega hole. We do have our earth. Okay, and in between we do have air which is actually acting as dielectric material, and whenever there is so much huge amount of voltage created in the clouds, it breaks the air as a which is acting as a dielectric medium, and it gets shorted to the earth. Lightning. Okay, we have seen this phenomenon. The dielectric strength is the maximum electric field that a dielectric can tolerate or withstand without electrical breakdown. Dielectric strength, उसकी strength कितनी है भाई, यहाँ पे 10 मेगा वोल्ट लगाओ तो लाइटनिंग होगी क्या? नहीं. ओके फाइन. अगर 11 लगाता हो तो लाइटनिंग हो रही है. Means this 11 let us say kV per meter is your dielectric strength. This is for an example, just that's it. Okay. Then we do have different types of dielectrics as well, depending upon their nature. We do have linear, isotropic, and homogeneous dielectrics. A material is a linear if d bar varies linearly with electric field. Electric field अगर बढ़ रहा है तो electric flux density भी बढ़ेगा. Materials for which epsilon, that is permittivity of the material, or sigma, conductivity of the material, does not vary in the region being considered. मतलब आपके पास एक rod है, okay, and inside rod there is, I will make some sections, first section, second section, third section. Okay, first, second, third. So let us consider the first region only. So यहाँ पे उसका permittivity या conductivity same होना चाहिए, being considered, the region being considered. Okay, the same at all points, that is independent of xyz, are said to be homogeneous. Okay, are said to be homogeneous. Materials are inhomogeneous or monohomogeneous when the permittivity of the material is dependent on the space coordinate, or permittivity vary हो रही है. Okay, And in some cases, in space electronics, we do consider this kind of materials for electronics. Okay, materials for which d bar and e bar, okay, are in the same direction parallel to each other are said to be isotropic material. All of these are just MCQs. Okay, you have to remember the definitions. Okay, then moving on to next, a dielectric material is linear if d bar is equal to epsilon e bar and permittivity does not change with applied electric field. Definitely, permittivity of the material is a material property and is not a property of externally applied electric field. But yes, under the influence of sufficiently high electric field intensity, your permittivity may get changed. And if it is not happening, then it is called as linear. Okay. A dielectric material is homogeneous if d bar and epsilon e bar and permittivity does not change from point to point. Okay. A dielectric material is isotropic if once again d bar is equal to epsilon e bar and e permittivity does not change with the direction. Okay. पॉइंट टू पॉइंट कहीं पे भी देख लो सेम ही होना चाहिए अगर सेम है तो होमोजीनियस है अगर इन अ सर्टेन डायरेक्शन इट रिमेन्स सेम okay in some different direction it varies okay it is called as isotropic okay everything in relation with the electric flux density electric field intensity and the property of the material permittivity okay now let us go with the numerical we do have some set of formulae okay? Epsilon r is equal to the relative permittivity is equal to ze plus 1 then d is equal to epsilon 0 e epsilon r e. It is also can be expressed as epsilon 0 e plus p, okay, where polarization p is also expressed as z e epsilon 0 e, okay. Then we do have another point, average dipole moment. This is for the sake of definition, the amount of polarization divided by the number of dipoles. कितने dipole create हुए हैं? And this is simple formula V is equal to applied electric field over certain distance. Okay? तो ये जो है फॉर्मूले आपके साथ रहने चाहिए and if you are read the numerical those are pretty much easy numerical just याद रखो this is relative permittivity okay this is electrical susceptibility ये wording बहुत ज़्यादा important है okay this is polarization तो अगर इतना आपको याद रहेगा तो you can definitely solve numerical very easily as said previously the approach we are going to implement while solving the numerical till date we have used given to find then what sort of formulae so we are going to discuss given what to be find I will give you set of formulae and this will be towards you put the values and get the answers okay so let us go with the first numerical find the magnitude of d bar and p bar that is electric flux density and the amount of polarization for a dielectric material in which electric field intensity the magnitude of electric field intensity is 0.15 millivolt per meter and the electric susceptibility Z is given as 4.25. So we do have all the notations in the numerical indicated for the first time. Means we are solving the first numerical. Therefore, those are indicated as notations in the numerical. So we have data E, we have ZE, and we are asked to calculate D and P. So straightforward set of formula. Epsilon 0 is equal to ZE plus 1. This will give us epsilon r. From there we can calculate D And we do have another formula to calculate the polarization, that is Z E epsilon 0 E. So this is simple 0.25. This is something 10 raised to minus 9 upon 36 pi into 5.25 into 0.15 into 10 raised to minus 3, and so on. The numerical is straightforward. You will have your answers. Next numerical. A dielectric material has electric susceptibility. That means ZE. Do you remember that? You are writing ZE as straight and a curve ZE, and it carries uniform electric flux density. Okay, this has to be meter square. Here you are given with electric flux density D. Calculate magnitude of electric field. Find magnitude of polarization. Okay, polarization talks about epsilon r, epsilon 0 and E. Okay. Average dipole moment, the formula is with you. If there are 2 into 10 raised to 18 dipoles per meter square. So this is a huge number. Voltage between two equidipoles if they are separated by 2 centimeter. The formula which talk about voltage. Okay. So straightforward formula, find epsilon r is equal to Ze plus 1. D is calculated as epsilon 0 epsilon r E. Okay. From here, we will get the value of electric field intensity, magnitude of electric field. That will be our first answer. Then polarization is equal to Ze epsilon 0 E. We already have the E, therefore we can have the P. That is second answer. Then average dipole moment is amount of polarization. Okay, this polarization, this value will be coming over here, and number of dipoles are given in the numerical, and voltage between two equidipoles. So इलेक्ट्रिक फील्ड इंटेंसिटी है आपके पास और d दिया है 2 सेंटीमीटर. Do remember that either you have to consider 2 raised to minus, oh, sorry, 2, okay, or you have to write down 0.02 meter. Accordingly, you have to take care of that measure since this is in centimeter. Okay, straightforward. Another numerical. If you have these two formulae, okay, these are the some different formulae. Then next, numerical 3, a parallel plate capacitor with plate separation. Okay, parallel plate capacitor T 1.8 millimeter has electric field. Okay, fine. If gap between the plates is filled with dielectric, epsilon r is equal to 2.55. Calculate magnitude of d bar, magnitude of p bar. Surface charge density of polarization charge. Okay, surface charge density of free charges on the plates, and the voltage between the plates of the parallel plate capacitor. Let us go one by one. So D is equal to, first, D is equal to epsilon 0 epsilon r E. epsilon r दिया हुआ है, epsilon 0 पता है, E भी पता है. We will get straightforward answer. Then P is equal to D minus epsilon 0 E. ये कहाँ से आ गया? If you remember, we talk about electric flux density increases. Previously, it was this much, and due to creation of polarization, electric flux density increases. So rewriting the formula D minus epsilon 0 E. So you do have D, you have epsilon 0, you have E, so you can calculate your polarization, magnitude of polarization. Then surface charge density of polarization means value of polarization, kitna hua polarization, that is you have already calculated. That is second part. Surface of charge density of free charges, something mistake, surface charge density of free charges on the plate means the value of D that you have already calculated in point number 1. And the voltage between the plates is V is equal to ED. E आपको पता है 22 किलो वोल्ट, एंड D is separation कितना है 1.8 millimeter. So 1.8 into 10 raised to minus 3 meter consider करना है. So these are just another type of wordings which are used instead of asking the direct terms in direct terms. मैग्नीट्यूड ऑफ डी नहीं कहेंगे, मैग्नेटिक फ्लक्स इलेक्ट्रिक फ्लक्स डेंसिटी नहीं कहेंगे. वो क्या कहेंगे? सरफेस चार्ज डेंसिटी ऑफ पोलराइजेशन चार्ज. they won't say कि भाई sorry they won't say क्या कहता है उसको पी बार नहीं कहेंगे ये शायद मैंने थोड़ा सा उल्टा पुल्टा लिख दिया so polarization means this one let me erase otherwise that will remain as it is let me correct it let me do it once again so surface charge density of polarization charge is magnitude of polarization and surface charge density of free charges on the plates it is nothing but your magnitude of electric flux density तो वर्डिंग्स में डिफरेंस है उसकी वजह से डिफिकल्टी लेवल बढ़ जाता है सो दिस वाज फॉर योर इंफॉर्मेशन थर्ड एंड फोर्थ पॉइंट टू बी कैलकुलेटेड दोज आर जस्ट सिंपल डी एंड पी let us go to next numerical number 4 a parallel plate capacitor has a surface charge density rho s दिया हुआ है find the dielectric medium between the plates epsilon r दिया हुआ है find the force in terms of surface area okay with which the plates of parallel plate capacitor attracts each other also calculate the pressure on the plates अभी ये तो नए वर्ड्स आ गए जैसे ही नए वर्ड्स आते हैं do remember that there has to be some sort of understanding about the standard notations so we do have electric field intensity which is expressed as rho s is equal to 2 pi epsilon 0 epsilon r a n cap electric field intensity due to your surface charge due to surface charge here what will be the value of a and cap we have to think about it okay another thing we are asked to find the force can be expressed as your amount of charge and electric field in which that charge is moving okay that charge is moving we have to talk about that then q is expressed as okay q is expressed as rho s into s since we are dealing with the plates we will have the surface and whenever we say that surface charge density that is total amount of charge upon the surface area or we can say that total amount of charge can be expressed as surface charge density into surface area okay so we have to think that way so we will put all the values in the expression of f bar okay f bar में q रख दिया e भी रख दिया okay so we do have some sort of values over there and means we do have rho s we do have क्या कहते हैं उसको epsilon r epsilon 0 still we don't have the surface area and a n cap but do remember that even if s is not known to us read the numerical फोर्स इन टर्म्स ऑफ सरफेस एरिया तो उसको वैसे ही रखने दो कोई दिक्कत नहीं है रहने दो उसको वैसे ही S and AN cap will be as it is we will calculate rest of the terms then pressure is force observed per unit area simple definition था force upon S तो जितना भी force बना आपका divided by S that will be once again in terms of क्या कहते हैं न्यूटन in terms of let us say surface but if you observe you do have surface term over here as well as surface term inside the expression of force so that those surface will get cancel out and you will get a value you will get a value so pressure on the plates okay so this was about the first of unit number 2 a little bit about the materials and the behavior of electric field okay behavior of electric field inside the materials okay so this concludes our today's lecture thank you everyone take care bye bye I am downloading the attendance fine. Someone left. I don't know who left from the lecture. Previously, there were 17 participants. Now there are only 16 participants. That's all for today's session. Everyone, take care. Bye bye. You do have next lecture. Bye.